Okay, so in this first bit of video, we're going to look at the construction of a design of experiments table. I'm going to start off by looking at the reason why we have to do all this stuff, because broadly that's because we need to compute the columns for certain factors that have been simplified in our design. Okay, so the problem with the fractional factorial design, which is here represented as a 2 to the 7 minus 3 resolution 4 design, is that we've gone down from 128 experiments 2 to the 7 down to just 16 experiments 2 to the 7 minus 3. What this means is that for the first 4 columns, which is the 7 minus 3, for the first 4 columns I, J, K and L, we can use our simple rule minus plus for the first column and so on. Minus minus plus plus, factors of 2 as you'll notice, 4 minuses, 4 pluses, 8 minuses, 8 pluses, and then when we get to the remaining columns our rule doesn't work anymore because they would all be minuses. We curtail at 16, we can't keep going on. So therefore we look up in our table the 2 to the 7 minus 3 design solution for that particular case. Here it is. Resolution 4 in this case, 7 factors, 2 to the 7 minus 3, and we get these hieroglyphs here, okay, which are the rules for putting out columns 5, 6 and 7, the remaining columns. So column 5 is the product of the signs in columns 1, 2 and 3. The simple rule here is, of course, that if you have an odd number of minuses, the result is a minus. Minus times minus is plus, times minus is minus. I'm going to leave the 1 out, but you can imply it. So plus times minus is minus, times minus is plus. And we can keep going down this table, filling out the details as we go. Even, odd, even, odd, odd, even, odd, even, even, odd, even, odd, odd, even. For column n, it's the 6, it's the column of 2, 3 and 4, result of 2 and 3 and 4 multiplied. So we've got odd, odd, even, 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 odd, odd, even, even, odd, 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 even, even. And I'll leave you to do column O for yourself. Ultimately, at some point, we'll come across this particular design table. Within this, we have to choose a particular solution for the problem that we're faced with, based on the number of factors that we're investigating, which is K, down the left-hand side here, and then this thing called the design resolution, shown with the Roman numerals. So the rest of this short presentation will be looking at this problem and looking at how we solve analysis problems using this, how we can exploit it. It's important that we consider the interactions that can take place between factors. Now, the simplest interaction is in fact no interaction at all, to some extent. It's called a main effect, and you can think of this as a one-way interaction. And this is the net effect of one factor changing from its minus level to its plus level when all the other things are changing in your design. So we can isolate that single effect. So we'll have main effects for every one of the factors. Now, in these experiments, we are guaranteed to always be able to calculate main effects. We can isolate them from all of the results. The same is not true for secondary and higher order effects. So a secondary effect is a two-way interaction. It's what is the net effect of two factors changing simultaneously up and down when all the other things are changing. Above two-way interactions, three-way and so on, we tend to find in most cases that the effect is negligible. So in most cases we'll only be interested in two-way effects. Now the problem comes that because we're reducing the design, as we'll see, and as you will have seen in previous lectures, we lose some of the resolution here. We're unable to to isolate some of these higher order effects. So that's why we need to look at this table and understand what's going on with this thing called design resolution. Now we're dealing here with partly factorial designs. This is not the case if we've got fully factorial designs. We don't have to think about this in those cases. The trouble is, if you think about it, the fully factorial designs can become computationally very expensive, and we don't have time often to do them. So here we're reducing the number of experiments by a fraction p, and so we talk about half designs, quarter design, eighth designs for that reason. So the number of experiments is 2 to the power k minus p. K, we know it's the number of factors we're interested in. P is something we choose to get the number of experiments, bearing in mind we might need to replicate as well, down to a manageable size. So these additional factors, or these reduced factors, these fractional factors, the P here, cannot be, as we've seen, determined using our alternating minuses and plus rules. So we have to look in a table. The reason we need to look into the table is because of this confounding or aliasing of effects, which we can see in this diagram here, where you'll see this is a fully factorial design at the top. We saw this a few weeks ago in class, and all of the effects, and we'll talk about how we calculate these minuses and pluses here later on, all of these columns here, the main effects and the two-way interaction effects, are unique. Every column of minuses and pluses is unique. It's different across all these 6. And that's what allows us to isolate the effects of these from these, of these within these, although that's always the case, and between these. Now, if we look at a half fractional design for this same problem of 3 factors, but we've reduced it down to just 4 experiments, we'll find that the two-way interactions are confounded with some of the main effects. So if we look at column K, we'll see that the sequences of minuses and pluses is exactly the same as I cross J. And the same is for J with I cross K and for I with J cross K, which means that when we compute the effects, and we'll look at that in shortly in another little video here, we can't determine the difference, and that's the problem. They're confounded. And this is a resolution 3 design. So we use a little rule to determine which resolution we need in order to be able to see or resolve the information that we're interested in. So the general rule is that the resolution must be strictly greater than the sum of the ways. If we're interested in one way with one way, i.e. to isolate main effects, then 1 plus 1 is 2, and we need at least a resolution 3 design. The tables always show at least a resolution 3 design. If we're interested in isolating two-way interactions from main effects, that's 1 or 2 plus 1, that's 3, we need at least a resolution 4 design, and so on. If we want to resolve two-way effects from other two-way effects, so for example we want to know the effect of I cross J interaction distinct from J cross K interaction, then we need 2 plus 2, 4, we need resolution 5. So we use that information about the kind of detail that we want to extract from our results in determining which column to look up in our design table. So here's our design table, and for the case of being able to isolate or resolve one way with two-way interactions, we need resolution 4. So we'd be looking down this column, and if we've got 7 factors, then we apply this little rule here. And remember, the rule says that the signs in column 5 are the product of the pluses and minus in columns 1, 2 and 3. The signs in column 6 is the product of the signs in columns 2, 3 and 4, and the signs in column 7 is the product of the signs in columns 1, 3 and 4. That's all the rule means. Notice that this matrix is sparse, so there aren't solutions to everything. Now all of this is something that I said in a previous lecture, so this is just the warm-up to now look at how we compute the main and two-way interaction effects, and for that matter higher order effects if we want to look at them.